penetrance, radiation behavior in the previous video. So whenever radiation emission takes place, it is subject to absorption, dispersion and transmission. But there's one more thing. The formula that is responsible for quantifying absorption, absorptivity, apart from A equals epsilon times concentration times L, which is mostly for spectrophotometric. Mainly for spectrophotometric purposes. There's also another relationship that deals with solid media. For solid media, you have the formula which is emergent intensity for absorption and transmission relationship. And that's the emergent, and then incident, and then that's the incident intensity, and it's exponential, and it's minus mu x, and if you lineate it, it would come out to be, so this is this one is emergent. It quantifies emergent radiation intensity in terms of its intensity, which is power per unit area. This one is incident. Sorry, this is the emergent. So this was the incident, the one that hit the medium. So incident intensity, and this factor is known as the linear absorption coefficient, which is measured in per meter, and this is the thickness. So, for example, what I'm trying to elucidate is if this was a block of aluminium, and you fired gamma rays at an intensity of 100 watts per meter squared, and the density of the thickness of this wall was 1 meter, and the coefficient was 100 per meter. The emergent intensity would be as follows. So 100 watts per meter, we always mention watts per meter squared, always mention the units, exponents, minus 100 times 1 meter, and then you multiply it, and you'd get you'd get 100 sorry minus 100 as well. You'd get 3.72, which is negligible, 10 to the power minus 42 watts per meter squared. So you fired 100 watts per meter squared, and out of the aluminium, which had a work function of 100 per meter, the absorption coefficient, 100 per meter, you were able to get emergent intensity of 3.72 times 10 exponent minus 42 watts, which is negligible. Therefore, emergent intensity is negligible, and absorption is high. So we have proven mathematically that if you take 1 meter thickness worth of aluminium and you fire an intensity of gamma radiation with 100 watts per meter squared at it, and supposedly if the absorption coefficient for aluminium was 100 per meter, then you'd only get a reaction of emergent intensity of radiation of gamma photons at 3.72 times 10 to the power minus 42 watts per meter squared, which is negligible, and the absorption for aluminium would be very, very high for the gamma radiation. So this is good, and so very, very little negligible emission and high absorption. Okay, and that's very important to realize. I've used a fictional number of I've used a fictional value for this this aluminium's absorption coefficient. It's not like that in real life. Aluminium's a beta absorber. It cannot stop photons of X-rays, gamma rays, UV, I think UV as well. Yeah, I think a little bit UVC. So it can't stop that. So I think, yeah, UVC can't be stopped. So please bear in mind that this is what the calculations would look like, and then this is what your inferred conclusion would be. You'd have to write this like this. Thank you very much for your time. I hope you understood it. If not, you are more than welcome to repeat this video, and I would suggest, to save time, play this video at 1.5 times the speed for efficient cost effectiveness. And I hope you were able to learn how to carry out calculation for absorption when pertaining to electromagnetic spectrum and different solid media. It could also be used for fluids, but I'm not too sure, because in fluids, the thickness of the vessel would interfere in the calculations as well. So I don't think we can use it for solids. So, but yeah, that's how things are. Thank you very much for your time, and I'll take it from here. Have a lovely day. Bye now.